Thank you, Nadav. And clapping before the talk begins. That's a nice touch. Well, I realize I'm the only thing standing between you and lunch, so I will try to keep it short. But yes, we're building a new lab in the Solid State Institute where we hope to study quantum science with trapped molecular ions. And just to give you a sense of the size of our ion traps, here's an example of an ion trap, and it's about 15 centimeters in size across. So this is the size our vacuum chambers will be around this. So the main question is, why study molecules in the first place? They're very complicated and hard to deal with, but they have a lot of advantages. Some of them relate to beyond standard model physics, so new physics in the sense that it's not included in the current rules that we have. And some of these, it turns out that molecules have enhanced sensitivity to CP violation. So CP violation is in charge of the matter-antimatter asymmetry that we see in the universe and is one of the biggest questions in physics today. Other examples of things that we can use molecules to detect is dark matter, which also relates to the CP violation in some ways. But we can also use certain molecules to study nuclear deformation. So very heavy nuclei will affect our spectroscopy of a molecule in a very sensitive way in comparison to atoms. And finally, we can use clock states in molecules to search for electron-proton mass ratio variation, which is also outside of the standard model. Another aspect that we've heard about today from Yaron is that molecules can actually help us make very nice qubits. And it's also been proposed that molecules can form qubits. So this is a D-level qubit, which can enhance the number of qubits that we have in a system by log of D. And the molecules can also serve as quantum memory because within the plethora of states, there are states with very long lifetimes. And so we can use them for quantum memory. It's also been suggested that we can use the dipole-dipole interactions of molecules to perform quantum gate operations. And so this is all of these are very promising things that we want to learn how to control molecules in order to take advantage of all of these different issues. Most obviously, we want to learn how to control molecules in order to study quantum chemistry. And that is to see phenomena such as tunneling resonances. And even more fundamentally, we want to control chemistry not with a knob on our Bunsen burner, but with a quantum knob of different degrees of freedom in there. So these are all motivations to study molecules. So how can we do this with molecules? They're so complicated. There's rotations and vibrations. And it's even very difficult to get molecules cold and trapped so we can begin to manipulate these degrees of freedom. So there are a few different solutions that the community has devised. Some of them are to build molecules out of laser-cooled atoms. So we take two laser-coolable atoms, we cool them both down, and we assemble a molecule that's very cold, and we can control its different degrees of freedom very well. And as you can see, pretty much, well, all of the combinations have been attempted so far, and there's still a few more to go, but this is a very promising direction to go. Another way to do it is to engineer a molecule that has a quasi two-level system. So that means that we can directly laser cool and drive the transition over and over again with a bit more than one laser. Usually it's around 5 to plug all the different holes. So here's a list of directly laser coolable molecules that are used. And as you can see, some of these molecules actually become very complicated molecules. And this is also a very interesting direction to go to. The problem is that in both of these cases, we're engineering the molecules to serve our cooling needs. And we're not necessarily picking a molecule that's useful for chemistry or new physics or quantum computing. Although these are actually probably pretty useful for quantum computing in that sense. So people have been trying to devise more general cooling schemes, and some of these schemes include just using a supersonic beam that cools our molecules, and the only issue there is that the molecules travel extremely fast at about 1 kilometer per second, and so you can build a decelerator type experiment that will slow down the molecules with magnetic fields, for example, and trap them in space. And these are actually very useful molecules, and it's a very interesting direction to go down. But what about molecular ions? Molecular ions?
This Segev over there.
Oh, this is a very talented Segev. Not the one in the crowd, but maybe even more talented.
My oldest son. His biological son, unlike very many other scientific sons.
So why ion traps? Sorry, I lost the chain of thought. Well, since we want to interact with a charge, we can actually build very deep traps for ions. So we can trap them at room temperature. And that means we can trap molecules because they can have a charge if we ionize them. So that's an exciting direction to go down. And another advantage is that we can co-trap them with another ion. And this other ion we can maybe laser cool, such as calcium plus. And if we laser cool a co-trapped ion, it'll cool our molecule by collisions and bring it down to a temperature where the molecules begin to crystallize, forming this Coulomb crystal, or what looks like a lattice. And this gives us the freedom to choose a molecule that is useful for our application. We can optimize our choice of the molecule to search for new physics. We can optimize our choice for building a qubit or a qubit. And it really gives us all of the freedom that we want. So here's an example of something that we can achieve with molecules where we have very long interrogation time in molecular ions. And this is an EDM search, an electrons electric dipole moment search. And what that means is that we're trying to measure if one side of the electron is more negative than the other. This is a search for new physics. And what you can see is by using molecular ions, we can trap them for a long time and measure a coherent superposition over 1.5 seconds. So this is already an advantage as opposed to neutral molecules where the records are well, they're actually pretty similar in some of these assembled molecules, but those are not useful for anything. Well, maybe so. I didn't say that. Oh, it's recorded. So we're building a new lab now in the Solid State Institute, and we want to ask, what other questions can molecular ions help us answer? What other things can this long interrogation time help us answer? And one of the fundamental questions is, why is life homochiral? Why are all the molecules that we see around us homochiral? And that means that if we look at DNA molecules in all of us, they all twist in the same direction, in the same clockwise direction. All the amino acids that we have in our bodies that make up DNA, that build DNA, are left-handed, and all the sugars are right-handed. And maybe this is pure chance. And maybe not. Maybe in an alternate world, we would all be of the opposite hand, and maybe actually this handedness was seeded by a meteor that hit the Earth at some point with chiral molecules. We know that meteors have chiral molecules on them, and we know that one-handedness has a preference there. But maybe the answer is a bit more interesting than that. Maybe it's not just that all the beastly grill is twisting right-handed. Maybe it's the weak force that breaks the symmetry between these molecules. And we'll talk about what that means in a little bit. But in general, what we're going to try to do is build quantum detection schemes for our molecules, because it's extremely important to be able to detect very small amounts of chiral molecules. This is also something that's being done in Olin Cohen's lab at this point with attosecond pulses, femtosecond pulses. But we're looking for a little bit of a different mechanism. So why is it important to detect the chirality? Well, a molecule such as limonene actually has different smells depending on the chirality. So one chirality, one-handedness, smells like an orange. The other handedness smells like a lemon. So this is a little bit silly to detect, but when we think about medicinal properties, we know that 50% of all our drugs that are manufactured are chiral. And we're pretty sure that in most cases, only one of the chiralities, one of the handedness, is the active ingredient that we have. In some cases, the wrong-handedness is actually toxic for us. And so it is important to develop these quantum schemes, and we'll see if we get to that. But I know that you're looking at this molecule over here. This is limonene, and it looks extremely complicated. So let's move to something a little bit simpler that we can discuss on a quantum level. And this is hydrogen peroxide, 4 atoms, H2O2. And we can describe it as a double well potential. So if we look at one of the chiralities, as we twist the atom, as we twist the 2 hydrogen atoms, they come closer together and we get a barrier in between the 2 sides. And on the other side, we get the opposite chirality and a well, and another well. So we know how to solve this quantum mechanically. The wave functions are the symmetric wave function and the anti-symmetric wave function. And the degeneracy is lifted by mixing with excited states. But that means that if we're thinking about the classical notion of this molecule, and we want to describe it quantum mechanically, it means that the left state is actually in a superposition of the plus-minus state. But I already said that there's an energy difference between them, and that means that they gain a phase relative at the rate of this energy difference. And so if we wait some time, this molecule will switch chirality. For hydrogen peroxide, this happens increasingly quickly, but this would be true for any chiral molecule. And so does that mean, oh, this is 300 gigahertz.
Oh, wow.
Yes, so this is very fast. It's really, you would see 2 side bands. It's not, you can't really think of it as a chiral molecule in this sense in our world. But we'll get to molecules where they should be chiral. So yeah, so after some time, we would expect it to switch from the left hand to the right hand, and this is very fast. But does this mean that if we trap a more complicated chiral molecule and isolate it from the environment, will it switch chirality? Well, Hund was very puzzled by this, and he came up with an explanation that said that really it's interaction with the environment that creates the classical form of the molecule that we think of today. Every time the molecule collides with the environment, the wave function collapses, and it stays in its handedness because the collisions happen far and often. So this is very different than the classical picture that we imagine today of a certain configuration of a molecule. But perhaps there is something different that's happening here, and if we trap a molecule, it will not morph into the opposite handedness. And about more than 60 years ago, an experiment was conducted by Chien-Shing Wu. I probably butchered the name, but this was an exciting experiment to measure parity violation in the weak force. So what she did is she took some cobalt-60, which is radioactively unstable, which is radioactive, and she polarized the nuclear spins of these atoms. And then she watched the direction of the electrons emitted when this decays, when this atom decays. And she noticed that the electrons only fly away from the direction of the spin. So this breaks parity because if we flip parity, the direction of the spin of the cobalt stays the same. It's R cross P. You get 2 minus signs and it stays the same. So this is the first natural law that we know of that breaks parity. And the thing is that it should also affect our chiral molecules. So if we look at parity violation, if we include parity violation in our Hamiltonian, what we'll see is that our potential actually becomes asymmetric. One well goes up and the other one goes down. And if we try to solve the Hamiltonian now, what we'll see is that our wave functions now resemble our classical wave functions, our classical description of the atom, in the case that parity violation is bigger than the energy difference between the symmetric and anti-symmetric states. And it turns out that this should be the case for more complicated chiral molecules. Pretty much every 5-atom chiral molecule, such as this carbon-centered tetrahedral shape, should be stabilized by parity violation. But we don't know. We've never measured it. We've never trapped a chiral molecule for seconds and seconds. Actually, in this case of this molecule, what we know is that if we were to form a superposition of left plus right, we would expect it to morph from right-handedness to left-handedness in about 10 seconds, which is easy peasy in an ion trap. We can easily trap ions for tens of seconds without them falling out. So we can actually think of a scheme where we use an achiral excited state to couple left and right-handedness to create a superposition. And there's, of course, technical limitations to this, and it's not easy, but we're going to try to do this in our ion traps. And it also turns out that if we measure this superposition state, which will oscillate at the parity violation energy, and if we measure it, we'll have measured parity violation for the first time in a molecule. It turns out that measuring this frequency could actually be sensitive to dark matter. So there are certain types of dark matter that we can detect with this kind of measurement. And we started the collaboration with Yotam Sorek at the Technion and Gilad Perez and at Weizmann. And we're trying to see if this is really has advantages in measuring dark matter in this way. But we're also thinking about using a superposition like this as quantum memory, because it should have a very long T2 time. The T1 in molecules is always a problem because you're very sensitive to black body radiation. But yeah, this is it. We're building a new lab. If you're interested, we would love for you to come down and talk to us about our work. And I didn't get a chance to tell you about our quantum detection schemes for chiral molecules that we're developing that are more imminent in terms of the results that we expect rather than the precision measurement of parity violation. And we also have ideas about doing some quantum scattering experiment, doing quantum chemistry with molecules, molecular ions in general. So thank you for your attention. And any questions?
Thank you, Yuval. Questions?
Yes.
So in these precision measurements that you want to do, you need to have precision calculations, right, to compare to, because you're talking about very complicated potentials that you have to solve the Schrödinger equation for.
So
Who's going to do that?
there are people doing precision calculations on these things. The problem is that you can usually calculate molecular orbitals maybe down to the 1% level for these complicated molecules. Probably not even that. But the question is if you can do something a little bit smarter. For instance, we really do only flip the mirror symmetry. It's sort of doing a perturbation theory, and you don't know the calculation of your molecule very well, but perhaps you can do a switch on this and get and extract some information. And this is one way to do this. But yeah, this is the answer to your question. But to measure a non-zero result would already be pushing us in this direction.
You want to calculate the tunneling rates between left and right, right?
Yes.
And that's very, very sensitive to the potential that you need to calculate. So
Yes, but parity violation is different than the tunneling rates. That's separate, and that can also be calculated from these different respects. So first, I would say measure something non-zero at this limit, and then we'll talk about the theory to talk about. But you're right, this is a challenge, and this is a main challenge to use this as a test of the standard model. But for instance, if we're talking about dark matter, what we're really looking for is to measure parity violation and then to see an oscillation in time of this measurement, rather than to compare to theory directly.
So if one looks, I mean, one knows a lot about the weak force. So what is the scale of the weak force on the angstrom in atomic units?
So I can give it to you in hertz. So for a molecule such as this 5-atom molecule, CHBr-CLF, you're talking about a 100 millihertz shift of the weak force. And if you switch, for example, the center of this molecule with a uranium atom, it can go up to 10 hertz of a change. So this is kind of what the theories are talking about here, is that maybe in the early universe we had some heavy metal compounds that increased this. Maybe there's the magnetic field dependent parts that violate parity, and there were regions in space with very high magnetic fields that made this very significant. But yeah, this is if you're trying to compare it to 300 Kelvin today, it's not very significant. That's why we have trouble measuring it.
Thank you. Okay. Thank you very much, Yuval. And with this, we'll conclude this session. I remind you, we are locking this room, and after lunch, we're going on an excursion. Thank you so much.
Thank you.